So yes, this is a course in which I will focus on a particular example of eigenvarieties. Eigenvarieties in general parameterize, in some sense, some p-adic variations of automorphic forms. We're focusing on the first historical examples of such eigenvarieties, the eigencurve that was constructed by Coleman and Mazur. Because here the crowd has a pretty broad background, as far as I understand, I will not assume that everyone is familiar with overconvergent modular forms, so I will try to give a somewhat honest presentation of the construction and then focus on some geometric properties. So I'll just briefly say what the structure of the lecture series is going to be. So for lecture 1, we are going to talk about some ingredients of the construction. So we won't quite get to constructing the eigencurve, but we'll talk about Eisenstein series with the famous Q expansion given by the constant coefficient that it can be expressed in terms of either an L value or a Bernoulli number, as you prefer. And for the higher degree coefficients, we're going to write sum as d divides n of d to the k minus 1 q to the n. So this is a modular form of where k SL2z with rational coefficients. This is often called k minus 1 of n. Great. So we are going to now discuss the constant coefficient and the higher degree coefficient separately for a moment. So what can we say about both? So for the first, the constant coefficient, we have the very famous Coleman congruences as the weight varies. So I'm going to fix a weight if k is a weight such that p minus 1 does not divide k, then if I can take k prime congruent to k mod p minus 1 times p to the n, then I get a congruence involving the Bernoulli numbers divided by 2k. More specifically, I also get an extra factor. Does not divide. Yeah, perfect. Thank you. I need this assumption, otherwise this guy is not going to be p integral, so it doesn't make sense to say that. This will come back later. So these guys are congruent modulo p to the n plus 1. In particular, if I have a congruence modulo p minus 1 here, then I get a congruence mod p between these two guys. So these are the ingredients used for the construction of the famous Kubota-Leopoldel function, which interpolates these guys. On the other hand, there is also a congruence that involves the higher degree coefficients. So this is much more elementary than the Kummer congruences. So for higher coefficients, as long as we can guarantee that p does not divide d, then under the same assumptions for k and k prime, we have the d to the k minus 1 is congruent to d to the k prime minus 1 mod p to the n plus 1. So this is very elementary. This is just Fermat's little theorem applied to this situation. This suggests that maybe what we had originally written doesn't quite interpolate p-adically, but if I change this a little bit by adding the condition, and I'm denoting it with a p here, that p does not divide d, then we are in a much better shape for p-adic interpolation. And indeed, this is the observation that Serre made in his construction of a p-adic Eisenstein family. This whole thing can be packaged as a congruence between a slightly modified version of the Eisenstein series that I had written over there, plus 1. What are these Eisenstein series with this correction? Conceptually, I can write down their expansion, but conceptually they are Eisenstein series of level gamma naught p, which have the same systems of Hecke eigenvalues as Ek away from p, but importantly, for the operator at p, up, they have eigenvalue 1. UP eigenvalue. So from this example, we see a number of interesting things coming up. So there is a hope that things interpolate in p-adic families, first of all, that there is a condition on the congruence that is modulo p minus 1 times p to the m, which is the order of the unit group of z mod p m plus 1 z, which suggests that maybe the correct place to look at for congruence is something that has to do with the invertible elements in ZP by taking a limit. And the other thing that we notice is that we actually need to look at level gamma naught p, and we need to look at what we're doing with the UP operator. There is another Eisenstein series at level gamma naught p with the same system of Hecke eigenvalues as Ek away from p, which has UP eigenvalue equal to p to the k minus 1. And for that one, the story is a little different, and we'll come back to that later. Okay, so all right. So where are we? We'll see. So we need to make sense of a space where we can do this p-adic interpolation. And this is the weight space. So as I said, we expected the group of units in ZP to play a role. And indeed, we start with looking at the so-called Iwasawa algebra that I'm going to take to be the completed group ring of ZP units, which you can write explicitly as an inverse limit of this collection of finite group rings. Great, so this is called the Iwasawa algebra. just like finite group rings that parameterize for an abelian group the characters of the group, this guy does essentially the same thing, provided that we take continuous characters. So I'm going to take I'm going to define the weight space to be the rigid space associated, the rigid fiber of the formal scheme associated to lambda. I'm going to describe this much more concretely in a minute. But this essentially, by definition, satisfies the property that if I look at the CP point of this rigid space, they are going to parameterize the continuous homomorphisms from ZP units to CP star. Our goal is to reinterpret the notion of weight that we had in the classical world in terms of characters of this group ZP star. So how do we view this guy concretely? So, well, if I look at ZP star, it's not too complicated a group, so I can consider the principal units inside it. And write an exact sequence like this. This exact sequence splits, and the split is called usually the Teichmüller character. Which takes an element in Z mod P, Z units to the root of unity that reduces to that mod P. And I will view this as I can view it by composition with slight abuse as a character from ZP star to ZP star, just with finite image. So this is one bit of the picture. The other bit is this part here, which 1 plus p ZP can be identified using p-adic logarithm and exponential maps with ZP itself. So this is a profinite group that is easy to describe as well. In order to describe concretely the characters, so since this splits as a product, I can write characters to be a character of this times a character of this. And this results in a construction of the weight space in which I just need to interpret the characters of this guy here. But this has a concrete identification because we said that this is isomorphic to ZP as long as I take a profinite generator. I can write this as ZP double bracket T, so this is just formal power series in the variable T, and send T to 1 plus P as a group ring element minus 1. This is not a particular canonical identification, but you could take any profinite generator and do the same thing. Great, so then we just need to understand characters of the finite part and characters of this, which provides a description of the weight space as a disjoint union parameterized by characters of Z mod P Z that in practice are just powers of the Teichmüller character that I've defined as W chi. So this W chi will be a connected component, but it will be essentially the rigid space associated to the formal scheme attached to this, which is nothing but a unit disk. Okay, so where each W chi is a unit disk. Great, and because of how we defined this whole thing, we started with this completed group ring. So this comes equipped with a universal character of Zp star into the Iwasawa algebra. I'm just going to call it kappa going forward. And these can be viewed as functions over this guy over here. Now, when I do this, I said that I want to switch point of view from classical weights to characters here. Well, I need to identify what those should correspond to. So I'm going to view the integer weights inside W by taking a k to the character psi k that sends Zp star to itself. Well, I guess we are taking the type to be Cp star, and takes an element to itself raised to the power k. So this is a reasonable way to consider our classical characters. In general, here characters can be a combination of can be all sorts of things, first of all, but there are certainly natural characters that are obtained by multiplying characters of this form by a character that is factors through a finite quotient of the units in Zp. So there are weight characters in a sense. There is some Neben type that we can think of as well. So with this setup, there is an Eisenstein series that parameterizes exactly the EKP as before. So I'm going to call it E kappa and write this as formal Q expansion. There is work, of course, to understand exactly how to interpret the constant coefficient. This is the subtle part of the picture. I'm going to call it zeta chi over 2, and this should be thought of some sort of p-adical function. And then for the other coefficients, our work is pretty easy because we're just going to write kappa d, the inverse q to the n for d divided n. Yes? Huh? Hmm? This is a character, kappa. Oh, sorry. Sorry, thank you. Thank you very much. Yes, I meant a finite order character of the script. Thank you very much. Yes, this. So, okay, which port do I want down? That's 1, guess. No. Okay. Okay, so what is the conclusion here? Well, this Eisenstein series, to be precise, is too high. Oh. To be precise is defined over maybe we're just going to take a union of components. So I think this is correct, hopefully. I'm going to take the powers of the even powers of the Teichmüller character. This is for parity reasons, and I want to exclude the component in which the power of tau is just trivial. For the same reason, I don't want to take p minus 1 dividing k. Okay? So what is the property that interpolates Ek at classical weights, which are exactly the image of that map that embeds Z into the weight space. Under this embedding. So, sorry. This is a concrete example of a family. In general, unfortunately, we are not going to be able to write that many examples of family, just interpolating classical things. But we will have to switch our perspective completely and construct a big space interpolating this type of families that is a little bit mysterious, but we can prove some geometric properties of it. And we can prove that some classical forms can be put into these p-adic families. In order to do that, yes? P, oh, I forgot to say that, yes. P is always odd in anything I say, unless I say otherwise. Sometimes it's not 3 either. Okay. Thank you, yeah.
And also the interpolation is of that EKP.
EKP, yes. Thank you very much. Yes, this is an important point. This is the one that interpolates, not EK. Yes, great. So, yes. Hmm? Yeah? Sorry.
He's just asking what's written underneath the sum.
Oh, that's a good question. I also wrote it wrong. The D divide P does not divide D. Wow. Okay. P
Would you write explicitly what does interpolating mean?
Yes, so that's a good point. Interpolating means that, so when I define this character here, as I said, that corresponds, because weights corresponds to maps to CP. So I can interpret that K as a map here. The coefficients live in the Iwasawa algebra. When I take this composition with CP, I will get this formula here. That's what it means. This map is called the specialization map. Specializing a way K is what we say. Which can be traced down very concretely once you write down these isomorphisms. Okay? So, right. So as I was saying, we will not be able to just write families down. And we will also need to consider spaces of modular forms that are not necessarily classical, even when we want to work with classical weights. So I'm going to do that now. The big question is, what is the correct space of modular forms that can satisfy a reasonable spectral theory that allows for interpolation? Yes, so also an important point that I should make is, if you look at the family that I wrote down, this is not just a family of modular forms, it's in fact a family of eigenforms. It's a family of eigenforms for all Hecke operators away from P, and UP as well. In general, we will use spectral theory to construct these families, so we need to define reasonable spaces for that. So, for this next part, I'm going to assume that n is at least 5, P is a prime that does not divide n, and I'm going to assume that P is also at least 5 for different reasons. And none of this is super important. These are just simplifying assumptions, but the setup can be made to work in our settings as well. So I'm going to write x gamma 1n for the modular curve of level gamma 1n, which I want to think of as a scheme over ZP. So what does this classify? On the complements of the cusps, it classifies pairs of elliptic curves and a level and structure that I'm going to view as a map from the multiplicative group mu n into E. This level and structure is going to play no role in the discussion, and in fact, I'm going to drop it from the notation whenever I can. I'm choosing this level and structure first because we want to work with arbitrary ends in general, and I'm going to choose it to be at least 5 so that this is a fine moduli space. That's all. And on the other hand, we're also going to consider another moduli space, the modular curve of level gamma 1n intersect gamma naught p, also over ZP. Here I need to be more careful with defining my level structures, and I'm going to say that this is classifies away from the cusp, the triples as above, plus an extra piece of data, which is this H, which I view as a subgroup of EP, the P torsion, which is finite, locally free subgroup, of rank P. In what I'm going to describe now, there is going to be an interplay between these two modular curves when I view them as rigid spaces. In some ways, we could define the whole theory over here, but to have a good spectral theory, we'll need to consider this instead. So this is the role that these two modular curves are going to play. And I'm going to consider, so I'm going to call this guy x, this guy I'm going to call x prime, and I'm going to use the notation of like calligraphic x and x prime for the rigid spaces, rigid analytic spaces attached to these two guys. In practice, this essentially means you can consider the CP points of these guys, and you can discuss inequalities between functions and define open subsets that way on these spaces. Okay, and last piece of notation, omega is going to be the usual automorphic line bundle. Which is obtained by looking at the differential of the universal elliptic curves and pulling back along the canonical section. Looking at sections of this guy gives you, in the classical sense, gives you modular forms. In fact, it's also true that you can view this guy in the rigid world, take sections, and obtain the same thing. So we are going to use this fact that I can view the section of either of these groups as classical modular forms with coefficients in, no, what am I trying to do? Sorry, I'm getting confused about what I'm trying to write. And if you're confused about what it means to consider classical modular forms with coefficients in QP, you can just take this to mean take classical modular forms over C, look at the Q expansion over, there is a basis for the space over Q and tensor up with QP. So the statement is you can recover this in this rigid world as sections of this line bundle. Okay, we're going to draw a picture because this is going to be helpful to us. So we are going to start working over here, and then we'll translate the picture over from x to x prime. So the nice thing of, there is a very specific way of drawing this picture that I think is going to be useful to us. So we are going to look side by side at, on the one hand, the rigid space, and on the other hand, the special fiber of this over FP. And there is a relation between that corresponds on points to essentially just reducing mod P. Okay, so maybe I'll start with the special fiber. So I'm going to denote this as, can you see here? Is that okay? X bar. So this is going to be x over FP. So this guy, so this parameterizes elliptic curves over like extensions of FP with this level structure. We are going to ignore this level structure. And notice that over FP, elliptic curves are either ordinary or supersingular. And in fact, there are only finitely many supersingular elliptic curves that I'll draw like this, supersingular points. So that I can write this x bar as the union of the points for which the elliptic curve is supersingular, denoted as SS, and the points for this which the elliptic curve is ordinary. Okay, so this whole picture can be, I'm gonna need another board. one. Okay. No. Okay, so I can erase with these. What is this? Oh, no. Thanks, but no. There is already a lot going on here, I think. We can do that in between lectures. Oh, okay. Unclear. All right. Okay. All right. Not the best, but I think I can make it work. So the important thing that might be useful to know here is this condition of being super singular or being ordinary can be read off using the Hesse invariant. So I can take A to denote the Hesse invariant. This is a modular form mod P. I could give the definition, but it's not super enlightening. But in a second, you will be able to forget about it unless, and if you don't know what this is, level SO to Z. So full level, level 1. And the point is that this locus of supersingular points can be reinterpreted as the zero locus of this Hesse invariant. What does this correspond to in the rigid picture? So this is a mod P picture. I'm going to draw some funny looking rigid fiber. And think of a reduction map between the two, which at the level of points tells you that you're going to take elliptic curves here, lift them to integrally, and then reduce mod P. This makes sense as generalized elliptic curves, maybe. Okay, so why did I draw this in a funny way? Because the pre-image of these points is going to be, via this reduction map, a disk that I'm gonna view this way. And this so defines two loci in the rigid space, in which I have, on the one hand, that the points reduce to supersingular elliptic curves, and on the other hand, the points reduce to ordinary elliptic curves. This is the ordinary locus. So this part is x ord, denoted sometimes. And this is the supersingular locus, which is a union of disks. Great. Why is it useful to consider this Hesse invariant? Because I can reinterpret now this ordinary locus by using a lift of the Hesse invariant, which turns out to be simple to describe. So I'm going to rescale the modular form EP minus 1. Remember that we had assumed that P minus 1 did not divide the weight early on, precisely for the following reason, that the constant coefficient, as I've written it, has a P in the denominator. So I'm going to rescale this by the inverse of the constant coefficient, so that the Q expansion starts as constant term equal to 1, and all other terms divisible by P. Turns out that this is a lift of the Hesse invariant, lifts the Hesse invariant to ZP, which gives us a way of characterizing the ordinary locus, but in fact it also gives a way of saying how deep we are inside the supersingular locus, and which is exactly what we are going to do now. So I'm going to denote, here I'm using, this is where I'm, in this statement is where I'm using the assumption that P is at least 5. You can make this work otherwise locally, but this is easier. Okay, and now, so here is the point. So if I'm going to take a slope, call it a slope, or a value between 0 and 1. This range is chosen so that 1 is the p-adic valuation of P. This picture involving the Hesse invariant makes sense mod P. In this region, we can define neighborhoods of the ordinary locus. We can extend the ordinary locus a little bit by taking the points such that take the x in our CP points such that I look at the p-adic valuation of EP minus 1 at the point, this lift of the Hesse invariant, and this is less than or equal to R. So if I take R equals 0, here I get the p-adic valuation of this object is less than or equal to 0, so it's 0. So it tells me that the lift of the Hesse invariant is invertible. And this is exactly recovering the ordinary locus. But in general, this will allow me to get a little deeper inside here. So what is the advantage of this point of view? So it turns out that if I take R to be 0, so recovering exactly the ordinary locus, I have my sheaf of functions, I can take sections of it. And so in general, I'm going to define the R over convergent forms to be taking sections of this X R of the omega to the k, and these are, by definition, what I call R over convergent forms. So that if R equals 0, they don't over-converge at all. They're just convergent. And in general, they'll converge a little deeper inside the disk. So a theorem of Katz tells us that if I take R equals 0, so I look exactly at the ordinary locus, this definition recovers Serre's definition of p-adic modular forms of weight k, if you've seen this before. Which is a very nice definition just in terms of p-adic modular forms are essentially obtained by taking p-adic limits of classical modular forms in terms of Q expansion. That's very concrete. And lots of things can be shown to be p-adic modular forms. The problem is, if we want to do a spectral theory over the space does not have a particularly nice spectral theory. It's too big a space. For example, when we noticed from the get-go that the UP operators played a special role in that theory. It turns out that if we look at the space of p-adic modular forms, because there is so much flexibility in construct p-adic modular forms, you can find, for any weight, you can just construct p-adic modular forms with arbitrary slope, which is, by definition, the p-adic valuation of the UP eigenvalue. So we need to find some spaces that are, in some sense, a little smaller and with a better behaved spectral theory. So this is the warning here. This is nice, but not nice enough for what we're looking for. The spectral theory here is wild. So we really want things to over-converge a little bit. When I talk about spectral theory and the UP operator, well, when I look at this picture, there is no UP operator because the level is prime to P. So we need to compare this with what happens at level gamma naught P, which is what I'm going to do next. Wow, I'm incredibly behind. But, okay. Right, so we continue with our picture. So now we are going to look at X prime and what the special fiber looks like. Okay, so again, these points again correspond to supersingular elliptic curves, but we now have two irreducible components. Well, I'm going to call them X bar M and X bar et al. Okay, so what do they correspond to? So these two components, when you remove the supersingular points, are going to be the pre-image of the ordinary part in here. So remember that here we are parameterizing the same data as downstairs, plus the additional datum of a subgroup of EP. So on the multiplicative part, this corresponds to this subgroup being chosen to be mu p. For the ordinary elliptic curves, there is one choice that is going to be isomorphic to mu p et al. Locally. And on the other part, which is the one that I denoted X bar et al., the subgroup corresponding to is it locally isomorph locally et al., as the notation suggests. So Z mod PZ. Now, again, we're going to look at what the pre-image in the corresponding rigid space is going to be. Okay. So here, the picture is going to look a little different. So it turns out I can visualize this way here. I will have two regions. One is going to be the pre-image of this xm, which stands for multiplicative, where the group is isomorphic to mu p, locally. And the other component here, which corresponds to, so this region corresponds to this, and this region corresponds to the étale part. In the middle, there are some annuli that reduce to the supersingular points. So this is a way of visualizing my picture as before. So here, there is an obvious map from this part here to this part here, which is just forgetting the group. In fact, on the ordinary locus, this map has a section which would be given by taking an elliptic curve and mapping it to the connected component, so the pair elliptic curve plus the connected component of the p torsion, which one can see maps the ordinary locus to the multiplicative part. The nice thing about this map is that actually this extends to characteristic 0 via the theory of canonical subgroups. And in fact, it's even better. It doesn't just extend over the ordinary locus, but it extends a bit into the supersingular locus as well. Okay. Let me do this into no. 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 Oh no, sorry. Okay, losing my mind a little bit. Which one do the middle? The middle, I want to come down. Yes, thank you. Yes, thank you. Okay, so here we are getting to the main point of this whole business, which is this theorem of Katz and Lubin about the fact that this map that I just described on the ordinary part of the special fiber lifts to characteristic 0. So in order to do that, we need to say to declare what choice of subgroup we have in the p torsion. So the theorem is that such a choice can be made. So we have to restrict the value of r to be less than p over p plus 1. Then there is a section of the natural forget of the forgetful map that is called canonical. Maps to x prime that takes E to some subgroup, the pair E and the subgroup that is by definition called the canonical subgroup. So you can take this as a definition of what the canonical subgroup is, and this can only be done for R not too big. So we can extend, which allows us to view this definition of overconvergent modular forms either as section over X or as section over X prime, because we're taking a section of the map. These two regions are isomorphic. We can do either. What is really important for our construction is the following property of the map, which is if I take E an elliptic curve that now lies in X R over CP, well, I can consider quotients of this elliptic curve modulo subgroups that are not the canonical subgroup. This is important when we think of the definition of UP. So if C is not the canonical subgroup, this one has a canonical subgroup, then I can ask, where does the quotient by C land? And this lands inside X R over P. So this is still over convergent, but we have to change the radius of over convergence. Why is this important? This is important for the following reason. So this in particular tells us that if you define, and in fact, this is going to be an exercise for you to do. So use this to show that the usual definition of UP via correspondence gives you a map from UP from MK over convergent of radius R over P to the one of over convergent of radius R. So the radius gets multiplied by P. The slogan is that the UP operator improves the radius of overconvergence. And again, why is this important? Because this is telling us a very important fact for the spectral theory, that if I want to define, of course I can define also UP operator. I'm going to keep calling everything as UP by taking R this radius R restricting to the smaller radius of overconvergence, and then landing here. This is a way of defining the UP operator by composition as above. One of these maps that we're composing being a restriction map. And these type of maps on the level of sections of sheaves over rigid analytic spaces are very nicely behaved. So this leads to the next point, which is, how much time do I have? 35. Okay. So I'm going to tell you about we're going to shift gears and going to talk about the spectral theory of operators that look like UP over Banach spaces. And why this bit is important. And so fundamental is what? Yeah?
Before you do that,
yeah.
can you maybe recall how you define UP?
Yes. Yes.
The connection to the
yes, that's a good point. So, if you...
Sorry for slowing you down.
No, that's okay. So, yes. So the key point when viewing this as a correspondence is that we are going to take, we have two maps from x prime and x, one that takes E and C, I'm always forgetting the extra piece of datum, to E, the forgetful one, and the other that takes the pair and maps it to the quotient. So this is what is used to construct a map on the level of sheaves, which involves taking the pullback under one map and the push forward on the other. I haven't written it down carefully in my notes, so I don't want to say exactly what it is, but basically you see that you will have to take essentially sums over the values of the function at the various points of this form, as C is not the canonical subgroup to define the map. So it will be important to understand where this guy lands. Thank you. So spectral theory. So what is the point of everything here? So this is a big space. Infinite dimensional space, we have Hecke algebras acting on it. We have the usual Hecke operators. We put them in an algebra. We want to make sense of the systems of eigenvalues for these operators appearing in the space. It's not clear at all that one can do this in general on infinite dimensional spaces. So what we're going to try to do is to use the special operator UP that we've discussed to sort of reduce this infinite dimensional space question to finite dimensional bits on which we can then make sense of a spectral theory. And when we define this Hecke algebra over the finite dimensional pieces that we construct through the spectral theory, then at that point we can make sense of systems of eigenvalues appearing there. So that's the main goal here. So UP is going to be our crutch to make sense of the Hecke algebra and its eigenvalues as a whole. So let me tell you about the spectral theory. So this is a piece of like p-adic analysis. K equals QP is going to be our base field. This can be done more generally as over a Banach K algebra, and there is going to be a lot of technical stuff to figure out then. M, but I'm going to stay over the field for now. Banach K module. So it's going to be finite dimensional, like an potentially infinite dimensional vector space over K, together with a norm. It's going to be complete with respect to that norm, and this is going to be compatible with the norm in K. This is going to be this guy in practice. Okay, so let me give you, I use this board. Two definitions. So we say that M is orthonormalizable if it contains what you would imagine being an orthonormal basis in the setting, so this is pretty intuitive, so a set of elements such that I can write every element in M as some coefficients multiplying AI. So this is infinite a priori, so it's not a basis as a vector space, with the limit as I go into infinity of AI being equal to 0. So this is the sort of basis concept. This limit you can make sense as over taking the limits over the. You can make sense of this. You can imagine this being indexed by n. It's not a big problem in practice. Okay, and the other important property is that this recovers the norm correctly in the sense that the norm of an element M, the Banach norm in the space, is going to be the sup as I is in I of the norm of AI. These AIs are elements in K, of course. So, obvious example that you should think of is the Tate algebra. This is essentially what the Tate algebra is, and this basis will be the powers of X. Next definition is phi from M to N is compact if so it's a homomorphism such that if I look at this guy inside the Banach module of the homomorphisms from M to N, this is the limit of finite rank operators. So operators whose image is finite dimensional. The image of the whole thing might not be finite dimensional, obviously, but it's good enough, that's the point. Obviously, all of these conditions are trivial when M is a finite dimensional vector space. This becomes interesting when it's not. Huh? No, sorry. Okay, thank you. So what is an example of this? And this is really the key point, and I think I'll end on this for today. So, the example is I'm gonna take the disk of radius 1 over as a rigid space and map it, view it inside the disk of radius p. So there is a corresponding map at the level of functions that is given by mapping the K algebra, the Tate algebra of Px to kx. Then this is a compact operator. So you can do this as an exercise if you're not convinced. What is the point that I'm trying to make here? This example is really quite similar to the one we've considered so far, because this is a map obtained by restricting functions. And the UP operator, we showed factors through a restriction map. So the conclusion is that you can maybe believe that UP, no, well, you should also say that why this makes sense. So this is orthonormalizable as, first of all, is a Banach space. Second of all, is orthonormalizable, and UP is compact on it. So when we take this for granted, we have a lot of tools in spectral theory that we can apply to it. And I'm just going to give, since I'm running out of time, I'm going to give you a brief upshot of what's coming next. So once we have something like this, we are in a very good position to get started on our journey of understanding systems of eigenvalues, because we'll see that a compact operator, phi compact, has attached to it a sort of infinite dimensional version of a characteristic polynomial that is called Fredholm series. Which I can, like, this doesn't make sense on the nose, but you can think of generalizing this more precisely rather than the usual characteristic polynomial. And the key point is that this Fredholm series can be factored into products of polynomials times another Fredholm series. This factors in, I'm going to talk about this tomorrow, in products of the form qx times x, where this guy is a polynomial. And the really crucial thing is, once we have this, we will be able to use this to get a corresponding decomposition of the space, the underlying space, as two pieces, one of which is finite dimensional, of the same dimension as the degree of this polynomial. And there, we finally broke down this infinite dimensional vector space into pieces that are more manageable, and then we can look at the action of the Hecke algebra over it. So what does that have to do with, can you take a minute to finish? Yeah. S is something else, is another. Well, we have to see where these actually land. So, huh?
So far you can take 2 plus 1.
Yes, maybe we want to do better than that, but you know. Yes. Okay, so that's a good point. Right. So what does this have to do with p-adic families, just to conclude, because it doesn't look like it has much to do yet. So we have constructed a weight space. This type of picture that I described here is basically imagining to do this construction of the eigencurve fiber by fiber over the weight space. So over the classical weights, I can imagine the construction being more or less what I've described to you. We will get pieces that are coming from the systems of Hecke eigenvalues. We're parameterizing all the systems of Hecke eigenvalues that appear, with the important condition that will come out tomorrow, that phi, this operator phi, will have to act invertibly in these pieces. And the eigencurve will then be obtained by doing the same construction, essentially, over affinoids in the weight space. And that will really produce families. Okay, and I'll stop here.